Now let's return to radioactive nuclei and study the quantitative behavior of the spontaneous disintegrations. Let's say we have a box of radioactive nuclei. We might ask the question, which one of the nuclei will decay first? It turns out it is not possible to answer this question since radioactive decay is quantum mechanical in nature and therefore a random process. However, we can model the decay behavior of a large number of nuclei. We know that if we start with n radioactive nuclei at t equals 0, then this number will decrease as time passes. The following graph shows that n decreases smoothly as a function of time and approaches 0 after enough time has passed. To help describe the graph, it is useful to define the half-life, or T1/2, of a radioactive isotope as the time required for 1/2 of the nuclei present to disintegrate. For example, radium-226 has a half-life of 1600 years because it takes this amount of time for 1/2 of a given quantity of this isotope to disintegrate. In another 1600 years, 1/2 of the remaining radium atoms will have disintegrated, leaving only 1/4 of the original number intact, and so on. In the figure, the number of nuclei present at time t equals 0 is n equals n0, and the number present at t equals t1/2, or after one half-life, is half of the original number, or n0 over 2. The number present at t equals 2 times t1/2, or 2 half-lives, would be n0 over 4, and so on. The value of the half-life depends on the nature of the radioactive nucleus, as it varies from nucleus to nucleus. Here is a table showing the value of the half-lives for different nuclei. Notice that the values range from a fraction of a second to billions of years. As time passes, the number of radioactive nuclei decreases, and we can talk about the rate at which this occurs. This is known as the activity, or delta n over delta t, and it will have units of disintegrations per second. Since the decay of any one nucleus is random, the activity will be directly proportional to the number of nuclei present, since the greater number of the nuclei, the greater the number of disintegrations. We can make this proportionality an equality by multiplying the right side by a constant. Here it is lambda, which is known as the decay constant. A minus sign is in this equation because each disintegration decreases the number n of nuclei originally present. The SI unit for activity is the becquerel, where 1 becquerel is 1 disintegration per second. Activity is also measured in a unit called the Curie, which honors Marie and Pierre Curie, the discoverers of radium and polonium. Historically, the Curie was chosen as a unit because it is roughly the activity of 1 gram of pure radium. In terms of becquerels, 1 Curie is equal to 3.70 times 10 to the 10 becquerels, which tells you that in 1 gram of radium, over 30 billion nuclei decay per second. By applying calculus to the curve in the figure, we can determine the mathematical expression that describes it. We find that radioactive decay is an exponential process given by the following, where n is equal to the number of radioactive nuclei present at time t, n0 is the number of nuclei you start with, and lambda is the decay constant. Here, lowercase e is the base for natural log. It is an irrational number with a value of approximately 2.718. You will want to check your calculator, as many of them have a button for e to the x. We can determine a relationship between the half-life and the decay constant by considering the following. Starting at t equals 0, and then after one half-life, or when t equals t1/2, we know the number of radioactive nuclei at that time must be equal to n0 over 2. We can make these substitutions into the exponential decay equation and get the following. Solving this equation for t1/2, we find that t1/2 is equal to log 2 over lambda, which is equal to 0.693 over lambda. We now have our toolkit of 3 equations for dealing with radioactivity problems. The first is the activity equation, and while lambda can have any units of inverse time, it must have units of inverse seconds when used in the activity equation so that delta n over delta t has the units of disintegrations per second. Our second equation for radioactive problems is the relationship between the half-life and the decay constant. And finally, our third is the exponential decay equation, which gives us the time dependence of the decay process.